Welcome everybody. Hello, good afternoon, good morning, wherever you are, whatever time it is. I was just browsing through the chat window and seeing where everybody was from. We have students just from all over the place. I want to welcome you today and thank you for coming out and joining me today. We are going to be discussing some CCNP topics specifically for Cisco. So thanks for coming out and joining me. I see somebody 4 a.m. in Sydney, Australia. Amazing. Thank you for awesome dedication to learning and to learning new things. So thanks for coming out. Hopefully, by the way, my audio volume is good. Hey, Danny. So I assume people can hear me. If that is not the case, if you're having any kind of issues at all, just refresh your browser. If you're having audio or video issues, and also for those joining me on our website, I'm going to go ahead and post a link to the direct YouTube stream as well in our chat roll. So if you're not watching from YouTube, if you're having issues on our website, then you can jump over there and do that from that side as well. So anyway, yes, thank you so much for joining me. My name is Charles Judd. If we haven't met, I'm one of the trainers here at Kevin Wallace Training. Some of you may be following me on my on my own CCIE journey. If you're not, I would love it if you would do that. If that's something that you're interested in. Thanks for all the compliments, everybody. I am growing my CCIE beard, so that's necessary when you're going deep into CCIE studies, I understand. So getting that going again. We'll see if I can catch up with Network Chuck. Don't know. I got a long way to go, but we'll see. But anyway, I'm one of the trainers here at Kevin Wallace Training. I love training. I love teaching. I love learning new things. I recently started on my journey towards CCIE, so I've been studying that. I've been posting multiple videos every week about the things I'm learning, about my study progress, some of my study tactics, and just general updates and accountability things. So if you haven't jumped into that and you're interested in that, I would love it if you check that out. You can find me on YouTube, on Twitter, on LinkedIn, Judd Charles W. You can search for me on all of those platforms and find me. I would love to connect with you if we haven't got a chance to do that yet. Also, an easy way just to find all of that is to go to charlesjudd.tech. You can find all of that contact information on there as well. So yeah, that's a little bit about me and a little bit of what I'm up to. Kevin and myself finished our CCNP ENCOR and ENARSI video training series earlier this year, and we really never got a proper send-off. When we complete some training, we usually will take time to have a webinar and just to teach some things about that. And usually, if you've been around, you know we have some special sales and discounts. Definitely have some of those for you, so stick around for that. But we're going to talk about a few topics. What are we going to talk about today? Well, as far as ENCOR goes, if you didn't get a chance to check out the agenda, as far as ENCOR topics, we're going to talk a little bit about SD-WAN, just from a high-level view about what that looks like, what kind of technology that is, what that looks like in an implementation manner. We're going to talk about SD access. We'll talk about Syslog. We'll look at NetFlow Theory, and then we'll jump into some command line stuff as well. We're going to look at a basic NetFlow configuration, which is necessary for ENCOR knowledge. We'll talk about IPSLA, and we'll look at a basic configuration for that as well. And then we'll talk about some ENARSI topics. As far as ENARSI goes, mainly I'm going to focus on BGP today. So I'm going to talk about the different BGP states and timers. We'll look at BGP multi-hop, BGP route reflectors, BGP path summarization. So all of those things, all of those BGP topics, we're going to be looking at in a lab environment at the command line. So lots and lots to do, lots and lots to talk about. And of course, I do have some special offers for you today. If CCNP is on your radar and you haven't jumped into that yet, then you'll definitely want to stick around for that. I will have replays available of this, but the offers that I'm going to throw out there today, those will end at the end of this webinar. So you definitely want to be around for those, but I will have class replays available. So having said all that, let's jump in. Let's jump into our training and take a look. We've got a lot on our plate today. So I've got so many windows open here, by the way. Let me just take time to sort through all of this. And I'm going to jump into our slideshow. So first up, we're talking about SD-WAN technologies. We're going to take an overview of that. Enterprise WAN connections. Those were originally designed to interconnect our main offices with our branch locations so that we could do resource sharing. And that allowed for sharing access to centrally located resources such as centrally located data or services or even applications. Now, traditionally, we used dedicated circuits to achieve that, things like MPLS or frame relay circuits. And although these did provide reliability and security for our connections, our modern networks, we need to kind of rethink that. We know that cloud usage is on the rise. Cloud is the new hot topic. It's the new hot thing. And so we need ways that we can simplify the management of wide area networks. And that's why SD-WAN or software-defined WAN, that's why this has been given a rise. As the name suggests, SD-WAN uses software to control or to manage the interactions between our branch locations and our central resources. And when we're looking at the function of SD-WAN, one of the big advantages offered is that there's no longer the need for what we call backhauling our traffic. If we take a look at a very simplified topology here, we can see that we have a branch location connected over an MPLS circuit, which is using a traditional WAN connection method, back to a data center on the right-hand side of our screen. At the data center, we have some advanced security inspection happening. In this traditional WAN setup, all of the traffic from the branch is going to be backhauled to the data center for security services. That would include traffic destined to the cloud or to the public internet, and traffic destined locally within the organization as well. So as you can imagine, this can cause a myriad of performance issues. It can cause delay depending on your circuit speed. It can cause bandwidth issues on the MPLS connection. And so that's why we use SD-WAN to address that. SD-WAN addresses this by its ability to interact with all kinds of different cloud applications. And we know, of course, that more and more our applications are going cloud-based. If you think of how cheap and easy AWS storage is now, we think of how Office has moved to the cloud. We think about things like Dropbox, Azure, many, many more. And so that means that hosting applications in either public or private clouds it's going to allow direct traffic between that cloud application and the branch location. And it does that rather than backhauling all of the traffic through a central data center. So that's the big reason that we're moving more towards SD-WAN. SD-WAN solutions can intelligently control the path of our traffic so that we can optimize that traffic flow and we can reduce unnecessary bandwidth in the network. Now, you might be wondering what happens to the security inspection services since that traffic is now being routed through the data center. Well, that's been addressed as well, since most SD-WAN offerings now provide end-to-end traffic encryption and inspection. Additionally, more and more next-generation features, we're starting to see more and more of those added, such as anti-malware and botnet intervention, many features that you would see on next-generation security devices. Another big advantage of SD-WAN solutions is that they provide what we call traffic transport independence. And in order to understand that, we need to understand the difference in an overlay and an underlay network. So we can see here an example of an underlay network. The underlay network is simply the physical network infrastructure that's responsible for the delivery of our packets. And when we talk about overlay networks, SD-WAN is a type of overlay network. And overlay networks, those you can think of those as a virtual network that's built on top of the underlay network, or it's built on top of the actual physical infrastructure. Overlay networks are not a concept that's new. Those have been around for quite a long time. Overlay networks include things like voice over IP or virtual private networks, which run on top of the internet. With SD-WAN with SD-WAN as the overlay network, This gives us transport independence. And by this, we mean that our WAN connections can be made up of all different types of connection combinations. We might have LTE connections, we might have serial connections, we might have wireless, MPLS. It really doesn't matter what's running as our underlay network, because SD-WAN solutions can intelligently and really coherently choose the best data transmission path. And for us, as network administrators, that's really good news, because it makes our job even easier. It just simplifies what we're doing. And so now that we kind of have an understanding about what SD-WAN is and why that's useful in a modern enterprise network, let's look specifically at Cisco's SD-WAN solution and a few common ways that we implement that. The ENCOR blueprint tells us that we need to know specifically about Cisco's SD-WAN solution. And when we look at an SD-WAN implementation, we again want to specifically examine the Cisco-based recommended solution. At the time of this class, this is Cisco's SD-WAN, which is based on Viptela. Cisco acquired Viptela in 2017, and that provides cloud-based SD-WAN. This is recommended to be used in conjunction with Cisco's DNA Center in order to leverage automation and virtualization capabilities. Now, within Cisco SD-WAN, we can break this down into 4 planes. We have the 3 that you probably are most familiar with: the data plane, the control plane, and the management plane. We know those from traditional networking models. And we have a 4th plane that is actually combined into a plane, and we call that the orchestration plane. So there are 4 different solutions within SD-WAN that are created to manage each of these 4 planes. First is Cisco vManage. And that's very, very simply just the GUI interface for managing the SD-WAN solution. This is where you would really perform things like configuration and monitoring and provisioning. And then there's Cisco vBond. Cisco vBond controls the orchestration plane. It takes care of that part. And the job of vBond is to understand how the network is constructed and to make sure that all of the interconnected components are able to work together. One of the big capabilities with vBond is something called zero-touch provisioning. And that means that when an SD-WAN capable router is connected to the network, Cisco vBond can remotely provision the router from anywhere without the need for us to take any action. So we wouldn't have to necessarily connect to that and begin any kind of configuration. If we're doing zero-touch provisioning, Cisco vBond can take care of that, which is a really cool feature. And then we have Cisco vSmart, and that resides within the control plane, and we think of that really as the brain of the SD-WAN solution. As policies are created on vManage by an administrator such as ourselves, the vSmart component is going to be responsible for the enforcement of those policies. And those policies would be shared with other SD-WAN routers and other SD-WAN locations as well. Routes from our branch locations would be received via the Overlay Management Protocol, or OMP. vSmart can use the known policies against those routes to help us control our traffic flow through the SD-WAN fabric. And finally, in the data plane, we have the WAN edge routers themselves, and those are responsible, of course, for establishing the network and for forwarding traffic. These devices can be either physical, or they can be virtual, or they can be a combination of both. So let's look at a common way that we might implement this here from a really high-level topology look. We see a sample topology here, and within that, we have a main campus location, we have a couple of branch locations, we might have a physical data center, and we might have a cloud data center. And you can see that all of those are interconnected through all kinds of various means. We see MPLS, we see LTE, we see satellite connections, creating this network of sites. And again, remember that SD-WAN is an overlay technology, so that's going to give us transport independence. In other words, it doesn't matter what the underlying network infrastructure is, as we see here. SD-WAN can work with any and all of that. So at each of these locations, we would have a WAN edge router, and these routers would form IPsec tunnels with each other in order to create the SD-WAN overlay network. That makes up the data plane that we discussed a bit earlier. Also, recall all of the control elements that we discussed earlier, which were vManage, vBond, and vSmart. We would have a secure control channel established between each of these elements and each WAN edge router as well, and that would be used for provisioning and configuration. As for the edge routers themselves, again, those can be either a hardware or they can be a software platform. Hardware platforms include Cisco vEdge routers running on the Viptela operating system and certain integrated services router and aggregation service router models. Virtual platforms include the vEdge cloud router running the Viptela OS and cloud services router models running iOS XE SD-WAN software. So a few options there. So that's just a really high-level overview of Cisco's SD-WAN solution. If you want to get some practical hands-on, I would recommend going out to the DevNet sandbox. I've went out to the DevNet sandbox myself. You can make reservations, and they also have some always-on versions of things like DNA Center. So if you're really wanting to look around in there and poke around, that's a really great way to do that. So that's a look at, again, Cisco's SD-WAN solution and an example of how we might commonly see that implemented in an enterprise network. Now that we understand the merits of software-defined networking, how that helps us to simplify our management and our configuration of our infrastructure, Cisco's taken that one step further with what they call software-defined access, or SD access. Let's run down a few advantages provided by software-defined access, starting with the features of DNA Center. DNA Center is one of the new topics that we see, and as a matter of fact, in all of our blueprints. We see that at all levels, all the way up to CCIE. And it's certainly a fairly large chunk of the ENCOR blueprint is some cursory knowledge of Cisco DNA Center. You don't have to have a super in-depth knowledge, but you do have to have at least some familiarity with the parts and how that works. So Cisco DNA Center is a key piece of the SD access solution, and that acts as a central point of management that's able to automate the deployment and the configuration of network devices. With SD access and Cisco DNA Center, network device configuration, again, that becomes automated. So whether you're deploying one or multiple new devices in the network, Cisco DNA Center is going to work as a central point of management and configuration, which is going to allow us for much faster deployments. Policy enforcement is another improvement offered by SD access. So rather than relying, if you think about how we traditionally do policy enforcement, one of those ways is through traditional access control lists. SD access uses something called security group access control lists, or SGACLs. These can be thought of really as a group-based policy that are much more scalable. So if you think about the way a traditional ACL works, those rely on IP addresses and subnets, and that can be really complicated, not only to maintain, but if you try to scale that to a larger network, or if you try to merge networks, that can get really complicated. And so the SGACLs used by SD access, they overcome that limitation through group-based policies. And so these policies are based on the client identity rather than the IP address. So a client would be given a specific identity. Maybe that's an identity based on a certain department that they work in, and that identity would follow them through the network. So it's a much more scalable way to do that. Now, network virtualization, well, actually, before we talk about that, one other thing that goes hand in hand with our group-based policies is the ability to securely segment the network in a very simple way. Since SD access is able to see the entire network infrastructure, both wired and wireless, it sees that as a single network fabric, then it's very easy to segment the network without having the need for all kinds of different firewalls or complicated access control lists. Network virtualization. That's also a big plus for SD access. This allows our single physical infrastructure to be separated into multiple virtual networks. Each of these virtual networks can have their own set of access policies created and enforced through SD access. We can break the SD access solution down into two main components. We have Cisco DNA Center that we've already mentioned. That provides automation and it provides orchestration throughout the network. And we have a piece that is referred to by Cisco as the campus fabric. So if you recall what we discussed earlier with underlay and overlay networks, we know the underlay network is our physical infrastructure. And so the campus fabric is what Cisco refers to in this case as the overlay network. Cisco specifically calls the campus fabric a Cisco validated overlay. So the campus fabric solution will ideally manage the network through Cisco DNA Center. Now, we can also manage it through CLI or through API. We can do that through the netconf protocol. We can do that through Yang, the Yang modeling language. We can do that in a lot of different ways. The reason that a campus fabric was developed is, again, it overcomes traditional campus network issues, things like spanning tree and layer 2 forwarding. And it's an improvement over architectures that we know, such as the traditional 3-tier or spine and leaf model. So campus fabric, we can really think of that as a next generation campus network where we have simplified management and simplified configuration. So let's look at a graphical example of this. We see our actual physical underlay network, and we see the campus fabric overlay network. The campus fabric is what provides our network segmentation. It provides our security features through the policy-based security groups that we mentioned earlier. And the security provided here, again, that's going to go beyond traditional routing and switching security capabilities. It can use things like, we can leverage actually even the Cisco Identity Services Engine, Cisco ICE. We can leverage that for contextual user information and for even more advanced security policies. But you can see in the overlay network, of course, this is a very small example of that, but our overlay network appears virtually as a much more simplified version of our underlay network. Now, we already mentioned that the campus fabric overlay can be configured through CLI or API, or it can be fully automated through DNA Center. We can do that both ways. So you can use a campus fabric solution and manually configure that without using DNA Center. However, you want to know that in the context of ENCOR and in the context of the Cisco world, that is not considered to be SD access. When Cisco defines SD access, they specifically mean that they are referring to that very specifically as being fully automated with DNA Center. If DNA Center is not used, then you simply have a campus fabric solution. That's what they would call a campus fabric solution rather than a software-defined access solution. So I know that's kind of splitting hairs a little bit, but that's some nomenclature that you do need to be aware of and that Cisco has very specifically defined. You probably won't be surprised to learn that there are also 3 planes of operation in the SD access fabric. We have the control plane, the data plane, and the policy plane. The policy plane is based on Cisco TrustSec. TrustSec helps to create the security groupings that we mentioned earlier so that policies are based on identities rather than IP addressing schemes. Remember, we talked about the advantages of doing that rather than doing that in a traditional way when we think of traditional ACLs based on IP address schemes. And then we have the control plane. The control plane is based on the locator ID Separation Protocol, or LISP. LISP is simply an addressing architecture that was developed by Cisco as a variation of node addressing. So rather than having a single numbered address identifier, such as an IP address, LISP creates two addresses for each node, one for its identity and another for the location where it's found in the network. So LISP is really just a way to simplify traditional routing and to streamline that. And then we have the SD access data plane, and that leverages a tunneling technology called Virtual Extensible LAN, or VXLAN tunneling. This encapsulation is what creates the SD access overlay network. This is UDP-based communication, meaning that any IP-capable device can forward the information. VXLAN encapsulation allows not only Layer 3 overlay networks, but it also allows for creating separate virtual network instances where separate policies can be applied and enforced. So the big takeaway here is you want to know that the control plane uses LISP data encapsulation, while the data plane uses VXLAN encapsulation. Both of these encapsulations are important to know about. If we break down a typical topology structure visually, we're going to see four distinct layers in the SD access architecture. We see the physical layer, and that's, of course, our actual infrastructure devices, routers, switches, our wireless infrastructure, maybe a DNA center appliance, maybe a Cisco ICE appliance. In the network layer, we would see our underlay and overlay networks. The underlay network, of course, includes settings and protocols used in the physical infrastructure for transporting data packets. And of course, the overlay network, that is our virtual network that's going to form a fabric of its own. As we talked about earlier, the overlay network is going to strip out some of the limitations and complexities of our network, and that's going to make a more simplified fabric. The tunneling that we see here is going to be, again, performed by using VXLAN encapsulation. Then we have the controller layer, and that consists of the Cisco DNA Center, and if we're using an ICE appliance, it consists of the Cisco ICE appliance will be found in that layer as well. We can break down Cisco DNA Center into two main structures. Those are Cisco Network Control Platform and Cisco Network Data Platform. Cisco NCP is used for automation and orchestration of the physical and network layers, while Cisco NDP is used to collect analytics and historical trends. That's also used by the management layer, and it's used by Cisco ICE, the information that's collected there. Cisco ICE is, of course, for identity and security services, and that's the piece that identifies and places our users into policy groups so that policies can be enforced throughout our fabric. And then finally, we have the management layer, which is the Cisco DNA Center user interface. This is essentially a centralized dashboard that's going to allow you to view and control your entire network through intent-based networking. And the unique thing with Cisco DNA Center, the unique thing here is that it provides really simple GUI tools for management and deployment, which means you don't necessarily have to know how to configure each individual network device in order to use this deployment method. Now, I don't recommend not knowing how to individually configure those and just jumping in with DNA Center, but that is one of the selling points. That's one of the things they advertise about that. But again, if you want to take a look at that, and by the way, the GUI isn't a new concept. This hasn't been invented with Cisco DNA Center. The GUI's been around for quite some time. As a matter of fact, I even like using the Cisco ASA Adaptive Security Appliance GUIs. Those are very handy. GUIs have been around for some time, but Cisco DNA Center has just kind of taken that to the next level. It's made a really nice interface. And again, that's something you can go to the Cisco DevNet Sandbox, jump in there, and take a closer look at that. So now let's jump into the implementation of that. Now that we understand why that's relevant, now that we know the required pieces of the SD access fabric, let's look at a common way we might see that used in a real-world enterprise environment. We can see at the very bottom, we have our end user devices. We have both wired and wireless clients. And the first piece that we want to examine for an SD access implementation are the fabric edge nodes. This is the layer that's going to provide user access through wired or wireless connections. Not only does this provide a connection point, but this also is where identity and authentication for users takes place. This is where Cisco TrustSec and Cisco ISE are going to be leveraged in order to enforce security policies and to place users into appropriate access groups in the network. These devices sit on the edge of the SD access fabric, so really you can think of these they operate functionally just as our normal edge switches would, our access layer switches that are providing access for our end users. Then we have what's called the fabric intermediate nodes. So these are simply internal routers or internal switches that are part of our underlay structure. They have no role specifically in SD access other than providing underlay services. And that would be using protocols maybe such as OSPF or EIGRP, for example. And also remember that the underlay network is not dependent on any specific protocol, and that can be a mixture of wired and wireless as well. So we do have that capability. And then we have what's called the fabric control plane node. Remember that we talked about the control plane using Lisp encapsulation, and it uses that for node mapping. We already said that Lisp contains 2 namespaces for each node, an EID and a routing locator. So this particular node would essentially be this fabric control plane node. I went too far back in my slides. Let me get back to where I was. The fabric control plane node, this is essentially going to be a Lisp server, and it's going to contain a database that would be used to resolve our lookups. When we're trying to map nodes within the network, the resolution is going to happen on the fabric control plane node. Fabric edge nodes, we looked at earlier, would provide the information to, well, I changed my slides again. I'm sorry. The fabric edge nodes that we looked at earlier that we mentioned, which are connections out to our end devices, those would provide information from the connected clients, and it would create and update mappings that would go back to our Lisp server, and that would be able to use, we could use those to resolve lookups from those nodes. So it's important to note that you'll want to choose fairly robust devices as your fabric control plane node. You'll want to have a good piece of hardware for that because those are going to be housing all of your fabric mapping. So you just want to be aware of the hardware and software requirements when you're choosing that particular node. And then we have the fabric border node. These are essentially a Lisp proxy tunnel router, and those are going to allow for external layer 3 connectivity to the SD access fabric. Those are able to communicate policy and identity information between separate domains. So if you have a remote office or if you have a data center, these fabric border nodes can pass the policy and identity information over to those domains and handle that. There are 3 types of fabric border nodes. We have internal border, default border, and anywhere border. Internal border are also referred to as rest of company nodes, connecting only to known areas of our internal organization or known areas of our organization as a whole. So these could be a local data center, those could be a wireless LAN controller or maybe a firewall, for example. And then we have default border nodes, which we refer to as outside border nodes. They would connect only to unknown external networks, such as the public internet or the public cloud. And those would be configured with a default route that would take us out to the outside world. And then we have anywhere border nodes, which are essentially a combination of internal and default borders, offering connectivity both to the inside of the organization and outside to the public internet. We can see the fabric control plane and fabric border nodes here are connected to our server room. And that, of course, will contain things such as our Cisco DNA Center and our Cisco Identity Services Engine appliance. Also, we can see a wireless LAN controller there. And so this is going to require that you have fabric-capable wireless LAN components if you're using that there. You want to have fabric-capable access points and fabric-capable wireless LAN controllers. Now, one difference to point out is that with traditional wireless deployment, it's very common to see that as a centralized topology in the network. And that means that the wireless LAN controller is going to be centrally connected to our network infrastructure, which we would have access points dispersed throughout the entire physical building. And in this model, when we do that, we see one of our access points down at the bottom. We see our centralized LAN controller in our server room. When we deploy with a centralized model, all of the control plane and data plane traffic from wireless clients is going to be tunneled through the wireless LAN controller using CAPWAP tunnels because the wireless LAN controller handles everything. We know that with SD access, the data plane is distributed using VXLAN. So in an SD access wireless deployment, we have a fabric-capable access point, and that's going to establish a VXLAN tunnel with a fabric edge node, as we see here, rather than establishing a CAPWAP tunnel with the wireless LAN controller. The access point must be directly connected to the fabric edge node in order for that to be possible. So the VXLAN tunnel is going to be used to carry data from the access point to the SD access fabric, where the overlay network would then take care of directing that traffic as needed. This is a much more efficient and a much more scalable process because the traffic doesn't always have to be carried all the way back to the controller in that model. For control plane traffic, that would still be carried back to the wireless LAN controller, but this is done using CAPWAP encapsulated inside of a VXLAN tunnel. So you still get the advantages of using the SD access fabric to carry the control plane traffic back to the controller as well. And of course, all of this is managed, orchestrated, and monitored by Cisco DNA Center, which again provides a GUI user face where we can create policies, where we can subdivide our network into virtual instances, and where we have an automated control platform that will help assist us with configuration and with device provisioning. So that's an overview of SD access and how we commonly implement that in an enterprise network, how that interacts with our traditional physical network devices as well, to help improve our networks. All right. The next thing we want to talk about before we jump into some command line stuff pretty soon, let's talk about Syslog. Syslog is one of those topics it's been around a long time. It's still in the ENCOR blueprint, so we need to know about it. The Syslog protocol is a method for transporting event messages between our managed devices and systems. This has, again, been around for a long time. It was standardized in 2009 by RFC 5424. It's widely supported on most all major operating platforms: Linux, Unix, Mac OS, Windows-based systems. And in fact, when we use a debug command in iOS, what we're actually seeing are those messages being sent to our console connection. So if we're using Syslog, one of the things I always point out is that it's very important I shouldn't have to point this out, but hopefully it goes without saying, but I will point it out that it's very important that we have our date and time settings consistent throughout our network through using NTP. If not, then our time-stamped syslog messages that we're using for troubleshooting, they're going to be inaccurate, and it's actually going to complicate our job. When we're trying to correlate our logs and examine events that happen in our network, it's just going to give us a much harder time. One of the best practices for implementing syslog is to store our collected log messages on a centralized server. Some of the popular options that are out there include things like Kiwi by SolarWinds, PRTG, and Splunk, just to name a few. There are lots and lots and lots of different solutions out there, ranging from free to paid. But the main advantage that you want to know about of having a centralized tool is that they're able to gather syslog records from multiple devices throughout our entire network to provide event correlation. And not only is this correlation process a best practice, but depending on the industry that you work in and the security compliance standards that might be related to your business, this kind of correlation is a lot of times mandated. So it's very important to know that. This correlation is one of the foundations for effective log analysis. And again, we have lots of examples of tools here. They perform this correlation in various different ways, but the overall function is essentially the same. It will help us to pare down the information that's being presented to us. If we have a really large bad event happen in our network, we can have a ton of syslog messages generated and being sent to our server. So being able to correlate those and sort through those, that's going to help us get rid of redundant information, and it's going to allow us to sort and view what's happening much, much more efficiently. One thing you definitely want to be familiar with regarding syslog are the message severity levels. And by default, we have 8 different severity levels. Those are numbered 0 through 7. And you can see those reflected here in this table. We have level 0, which is the most severe level, all the way down to level 7. Level 7 being just your normal syslog event, your debugging messages. Again, level 0 would be the most critical. Those are emergency events indicating you have an unstable system, ranging all the way down to 7. So that numbering system might seem counterintuitive a bit to you, so don't get confused by that. Level 0 syslog events are the most critical, whereas you might instinctually think that level 7 being a higher number would be higher severity, but that's not the case. We also have ways to represent which system process created the syslog event, and those are called syslog facilities. You can see a list of those available facilities here, again, per RFC 5424. So these can tell us if the message was created, let's say, for example, by the mail system. If we see a facility number of 2, then we know that the mail system had created that. The RFC standard outlines 3 different layers found within the syslog standard, which is the syslog content, the syslog application, and the syslog transport. So this standard is necessary to have so that our devices can create information that's able to be understood and interpreted very widely within our network. The content layer, of course, refers to the information itself that is within the syslog message. The syslog application is what generates and stores the syslog message, and the syslog transport layer is used to send the message over the network. So if we take a look at the format of a basic sample syslog message, we have 3 main parts to that. We can see the PRI, the header, and the message itself. So we can see that the PRI, or the priority, that's going to contain the facility and the severity code. In this example, we see the facility code of 10, identifying this as a security message, followed by a critical level 0 emergency indicator. So that's how we would read that. Next, we see the header, and that's composed of 2 fields. We see the timestamp at which the event was recorded and we see the host name, with this host name being that of the machine which generated the syslog message. And the third part is, of course, the actual message itself. This contains the actual information about whatever event has occurred, and we can break that down into two main parts. We have the tag and we have the content. The tag contains codes about which particular application and process ID is related to the event, and the content is going to be the actual message output. Syslog services, you also want to know that they use UDP port 514 for communication by default. So that's an overview of the format of Syslog and why that's useful to us. Let's look at NetFlow Theory, and then we'll look at a NetFlow configuration in the command line. This is another popular management protocol that is in our ENCOR blueprint. This was created by Cisco initially, and this is used to collect IP network traffic as it flows through an interface. This type of visibility into the network is going to give us a better understanding of how our traffic is behaving, and there's lots of reasons that we might use that. Some of the common network issues that NetFlow helps to identify are things like network bottlenecks. We can use NetFlow statistics to find top talkers in our network. Or in other words, top talkers refer to the devices that are using the most amount of information over our network. They're maybe going out to, let's say, for example, you have a user that's streaming Netflix. They're definitely going to be a top talker on your network if they're just streaming in the background constantly. We can also see devices using the most resources. Slow network performance can often be traced back to those devices that are overutilizing the bandwidth in an unnecessary manner, so we can identify those and free that up. Also, we can see issues related to policy changes or issues related to new applications that we've introduced in the network. We can see what type of load adding a service, let's say we added voice over IP. We can see what type of load that added to our network infrastructure. Or we can measure how the network policy changes have affected our traffic flows. A couple different ways that we can use and do those. We can detect unauthorized or problematic traffic as well. That can include things such as end users unnecessarily utilizing media streaming that could cause congestion, or maybe devices that are using WAN traffic that should not be doing so. And we can also use NetFlow. I went too far with my slide there. Let me advance back to that. We can also use NetFlow to identify security vulnerabilities and security anomalies on our network. So things like worm detection, that's possible using NetFlow. It's important to understand how NetFlow gives you information in this manner. So in order to do that, we first need to understand what an IP flow is. And this is where the flow comes from in the NetFlow name. An IP flow is unidirectional traffic, or traffic going in a single direction. So if we look at traffic crossing a router in a single direction, if we have traffic coming into a port and it's destined, let's say it's destined for a public web server, NetFlow is going to examine each packet for a set of attributes. And these attributes are often referred to as packet fingerprints when we're talking about NetFlow. Similar packets are going to be grouped together into a flow record. Attributes that use NetFlow we'll group these packets together into a flow, and we can see some of those attributes that are used here. We use the IP source and destination address, the source and destination port, the layer 3 protocol type, the router or switch interface, the type of service associated with the packet, all of those things. NetFlow can capture on an egress or ingress. So in other words, when we say ingress, we can capture traffic coming into a port, or when we say egress, we can capture traffic exiting a port, depending on how we configure that. All of the packets that have these attributes in common are going to be grouped together into a flow They're going to be condensed, and they're going to be placed into a database on the router called the NetFlow cache. This would contain the flow information, or in other words, all of those attributes that we just pointed out. And it would also contain things like the total number of packets in the flow and the bytes per packet. Once this is in the NetFlow cache, there are two primary ways that we can access this. First, we can simply do that through the CLI using show commands, which we'll look at in just a moment. That's useful if you are in need of some immediate information while you're actively troubleshooting. But obviously, this cache is limited, and that's not going to be very helpful in the long term if you're looking for an historical view of your network traffic. It does have its place, and it's great for troubleshooting. But to truly leverage all of the benefits of NetFlow, we want to export our data to an external NetFlow collector. That's the second primary way to view this information, and that's the recommended way to do that. A NetFlow collector is a device responsible for receiving, interpreting, and storing flow records. We could configure our router to export NetFlow records from the cache out to a NetFlow collector. And again, that's the recommended way to do that. These collectors have the ability to really powerfully analyze and correlate the data into detailed and intuitive reports, things like graphs and charts. And that's going to allow you to really, really easily see network issues in a visual manner. Tools like these include Passler's PRTG. You can see an output from that here. That allows you to monitor LAN, WAN, VPN, individual application traffic. It's got some really detailed reporting and alerting. PRTG is one that I'm most familiar with, that I've used in the past. But again, there are lots and lots of different collectors out there. When we're using a NetFlow collector, on average, 30 to 50 flows are bundled together and transported over UDP to a NetFlow collector, where the collector can analyze in real time and again also provide historical data. Based on the NetFlow version, the format of the exported data will vary slightly. The two main versions that I'll mention here are versions 5 and version 9. Version 5 is probably the most popular format right now, and the reason for this is that the format is fixed and it never changes. Lots of our older devices use NetFlow version 5. Newer ones are backward compatible, lots of those. So this is easier to read since it has a fixed format. And when I say it has a fixed format, I mean the order that it presents the data in never changes. So it's very predictable. So it's easier for most NetFlow collection and reporting packages to read. At the time of this class, version 9 is the newest format. That brings better security and analysis features, and it has the ability to accurately report on multicast traffic. The format for version 9 is dynamic, so it has the ability to change. And because of that, it requires what are called NetFlow version 9 templates. And these templates are sent to our NetFlow collector periodically in order to let the collector know what format the data flow is being presented in, so that it doesn't become confused and so that correct interpretation can happen. All right, having said that, let's jump out to a live interface. Let me bring that up and I'll get that screen going. Okay, we should have a live interface out there now. Uh-oh. All right, there we go. Should be able to see my console connections now. Good. Now we're going to take a look at how we can configure NetFlow just very simply on a Cisco router. You can see from the topology here that we have a subnet of hosts on the 10.1.1.0/24 network. Those are connected into a switch and eventually connected into gig 0/1 on the router. And we have our gig 0/2 interface connected to a NetFlow collector, of course. And this collector could be any number of collector tools or servers that are available, by the way. We've mentioned things like SolarWinds or PRTG, lots of different options out there. So first, let's configure our ingress interface for NetFlow capture, and let's take a look at our local NetFlow cache. And then we'll look at how we can configure the router to export those records to our NetFlow server, which you can see is setting at 192.168.10.5. So first on router 1, let's go ahead and go under global configuration mode. And if I say IP flow-export, and if I look at contextual help, you can see that under here we have the option to choose version. We have the version keyword. So if I say version, this is going to allow me to choose the version of NetFlow that I'm using. We see 1, 5, and 9. So version 1, that's obsolete. That's limited to IP version 4 networks without network masks and without autonomous system numbers. Version 5, again, that is by far the most popular because of the legacy support and the fact that the format of the exported data is always the same. So lots of our older collectors can handle that version. At the time of this class, again, version 9 is the most current. It adds lots of features that we already discussed. So I'm just going to choose version 9 here and hit enter. And now we can go under the interface where we want to capture NetFlow data. And we'll go under that interface just as if we were configuring an IP address on the interface. So let's say interface gig 0/1. You can see that is the interface that's pointing out toward our end-device subnet. That's the ingress interface for our 10.1.1.0/24 subnet where our hosts are. So let's use the keywords IP flow. And if we look at contextual help, we have 3 options. We can configure this for ingress, egress, and we have an option monitor. The monitor flow is used with flexible NetFlow, which we're not going to look at the moment. So in this example, we're going to talk about configuring this to capture both incoming and outgoing traffic, or in other words, both ingress and egress traffic. So let's say IP flow ingress, and we'll say IP flow egress to complete that. And it's as simple as that, really. Now NetFlow is going to capture data from this interface, and it's going to store that in the NetFlow cache. Let me actually break out of here, and we can verify this configuration with the show IP flow interface command. And you can see this is going to show every interface that we've configured for NetFlow collection. So again, in our case, that is only the gig 0/1 interface. And we can see that we have that configured for both egress and ingress traffic. So now we can actually see our local flow cache by saying show IP cache flow. And if we look at that at the moment, you're going to notice that it's empty. We see lots of zeros, 0 active. We don't have any packet distribution happening currently. And that's because we don't have any traffic coming across this interface at the moment. So I'm just going to clear a little bit of that off. And what I'm going to do is I'm going to jump onto every one of our PCs here. And I'm going to ping my router. I'm going to ping, actually, just to make that easier, I'll ping everything. Yeah, let me do that from each PC. So I'll say ping 10.1.1.1. I'm just going to copy that to make it easier. And what I'm going to do is I'm going to jump on each of these PCs. Go ahead and get those ready so that we're ready to paste those in. Hit enter. That's good. I'll paste it in PC2 and ping from there. And I'll ping from PC3 as well. Now back on router 1, I'm going to ping each of those individual PCs. So I'm pinging 10.1.1.10, 11, and 12. Now if I say show IP cache flow, you'll see that we have something much different. We can see all of our information here. Remember that if we don't configure a NetFlow collector, this information, again, is stored in our local NetFlow cache, and that's exactly what we're looking at here. Again, you can do this even with a NetFlow collector configured. This is a great way to see some immediate information in the CLI view if you're actively troubleshooting, but it's not ideal for a historical perspective, but it is useful in many cases. So the first thing I'll point out, notice we see the IP packet distribution, and you'll see that this is presented as a decimal 1.0. So what this is telling me is that 100% of my packets are between the sizes of 96 bytes and 128 bytes. That's why we see that 1.0 range. And that's exactly what we would expect, because if you remember, ICMP messages by default are 100 bytes. So that's why we see 100% of those presented here. So that's what we're seeing. A bit further down, you see that we were told at the time that I ran this command, we had 5 active flows, and we had 6 flows added. So all of those here, we can see also that active flows will time out within 30 minutes. Inactive flows time out within 15 seconds. So we do need to have fairly recent traffic. Again, this points out why this isn't great for an historical perspective. We need to have a NetFlow collector for that. So, but if we're simulating this in the lab, as I just did, that's why I had to do that really quickly. Or I could have also created a continuous ping to simulate that. Now, if we go back and down here to the bottom of our output, you can see the source IP addresses. You can see the destination IP addresses, all the information for those ICMP packets. So lots and lots of great information here. And if we want to manually clear that, by the way, we can say clear IP flow stats just to clear that out. And now if we say show IP cache flow, those are all gone. So if you're trying to clear that out just to see some fresh information, just a quick way that you can do that in your lab. And just really quickly, somebody asked what tool I'm using for simulation. I'm actually in Cisco Modeling Labs at the moment. That's what I'm labbing. All of my stuff today comes from CML. So now we looked at our local NetFlow cache. What if we want to export our NetFlow data to an external collector? We can do that very easily. Let's go back, I'll clear off a little space, go back under global configuration mode on router 1, and I can say IP flow -export, and contextual help is going to show us the destination keyword. So if I say destination, this is going to allow us to point to a collection server. So let's use the address we see in our topology, 192.168.10.5. And if we look at contextual help once again, you'll see we need to indicate a port number. Now, there are several common UDP ports used by default. Depending on the collector that you've chosen, those can all, it really depends on the software. Lots of different options there, lots of common ports. I'm going to use 9995 in my case. Some of those common and preferred ports would include 2055, maybe 9995, 9996, several ports that can be used. So again, you want to check with your specific collector to see which port it listens over. So if I hit enter, I'm going to break out of here, and I'm going to again jump back to one of our hosts. I'll just go to PC1. I'll just do that from one host this time, and I'll just really quickly going to just ping 10.1.1 again, router 1, and I'll say show IP cache flow. We see that in there. If I say show IP flow export, we actually waited too long. You see how quick you have to be. Let me run that again. There we go. All right. So I initially you saw that no flows were exported. That's because I waited too long to run that command. So I went to PC1. I pinged my router. Now you can see that 2 flows were exported in 1 UDP datagram. So those are the flows being exported to our collector. Again, we have 2 specific flows because these are unidirectional. They're going in 2 different directions. You can see that this is telling us the flow export version 9 is enabled. We see the destination of 192.168 .10.5 over port 9995. So we see all of that information. And of course, down here, if we had any sort of failures, we would also be able to see that information as well. On the collector side, all of this data would be aggregated and it would be sorted, and we'd have some really nice graphical outputs to help us interpret exactly what's happening in our network. So let's go and take a look at IPSLA theory, and then we'll also lab up IPSLA. IPSLA stands for IP Service Level Agreement, and that's a feature built into Cisco iOS that provides a way to monitor our network performance. And that is an active method, actually, for monitoring and reported, so we can report on our traffic in a real-time manner. Metrics that IPSLA has the ability to report on include, actually I went too far, let me go back to that so you can see that. We can report on connectivity, delay, jitter, packet loss and sequencing, response time, lots and lots of things we can report on. So this is a very, very common tool to use for service providers where they monitor a customer site. But it can be helpful for us as well when we're troubleshooting on our network or troubleshooting our own topology. The benefit of IPSLA is that it doesn't require a physical probe. Now, we can use a responder, but it doesn't require a physical probe in order to monitor those. It simply uses generated traffic to measure the performance of a network between two devices. Configuring IPSLA requires an IPSLA source, and optionally, we can have an IPSLA responder, depending on how complicated we're getting with our monitoring. An IPSLA source is going to generate packets and send those to a destination device somewhere else on the network. So this can be as simple as an ICMP echo or a ping that's used to continually test the reachability of a remote device. And that's a common way you might see that used in a service provider environment. The response from the remote device would have timestamp information, and that would allow the IPSLA source to make calculations. So it could calculate network metrics that would be of interest, such as the response time or how long it took for that round-trip traffic to happen. Optionally, we can configure a Cisco router as an IPSLA responder. That would allow for more advanced IPSLA request packets. Some IPSLA operations will work without a responder on the other side, such as ICMP or HTTP, while others won't. Now, in order for IPSLA to be effective, they leverage SNMP traps triggered by events such as connection loss or jitter or latency or packet loss. For any IPSLA metric, certain thresholds can be set. So, for example, we might set a threshold for the round-trip time metric. If we have a specific time that we say, okay, after this amount of time, we want to consider connectivity loss to this network. We can set those metrics, and we can set that threshold. And if our round-trip time went above the threshold, then an SNMP trap would be sent out to alert us. Also, threshold violations can be used to trigger other IPSLA operations. So you can nest these within each other. Lots and lots of things there. For example, the frequency of the probe could be increased to ensure that the information is accurate and not just an anomaly. So, and again, an additional and optional piece of an IPSLA configuration is some type of SNMP agent, and that would give you the ability to read and interpret IPSLA reporting. Some of those popular options include, again, things like SolarWinds, PRTG, and NIGOS Core. But again, many SNMP monitoring tools are available on the market. Those are, again, going to provide intuitive reporting from a centralized location. So let's look at an example of this. Let's jump into an IPSLA command line. Now, this is a very basic IPSLA that we're going to look at. This particular example is not going to use a responder. We're going to look at a very basic configuration that will use an ICMP echo function to check for reachability of a device on the network. Now, I'll also point out that IPSLA is a deep subject, but we're keeping that at a CCNP ENCOR level here, and we're going to look at some basic configuration steps. You can see from our on-screen topology, again, we're really simple. We have a couple of interconnected routers, and we have a server. You can see the server is sitting at 10.0.0.6, and we're going to create a very simple IPSLA to check the connectivity status on this server. You can verify that your particular device supports a specific IPSLA function, by the way, by running the command show IPSLA application. And from here, we're going to see a list of supported operation types. And those might be different depending on your device. Not all IPSLA operations are supported on every device. So that is something to be aware of. We can see our supported operation types here, which are fairly numerous. So again, we're on router 1. Let's go under global configuration mode. And we want to start with the command IPSLA. And if we look at contextual help, at the top of that, you'll see that we need to give this an entry number. And that is really just so that each IPSLA probe we configure is individual. So it has its own individual identity. That's the same type of concept you would see with lots of things such as OSPF process IDs, for example. So we want to give this a unique number. So I'll just start with 1 in this case and hit enter. And now you'll see we're under IPSLA configuration mode. So now, if we look at contextual help again, we see all of our available operations here that we can configure. In our case, I've already said we're just configuring basic connectivity. We're going to test that basic reachability. So we can use this keyword we see here, ICMP-echo. And we need to follow that with the IP address or the host name for the destination that we want to monitor, which of course in our case, if you look at our topology, is 10.0.0.6. And if we look at contextual help again, we have a couple of optional keywords here. We can specify the source IP address. So if we want to specifically mark these ICMP packets from a particular source, we can do that. Or we can specify a source interface as well. We can do both of those. In my case, I'm not going to bother with either of those options. I'm going to hit enter, and then I'm going to continue. Now you'll notice that we're under we're under IPSLA echo configuration mode. So now we're setting our options for the ICMP echo function. If we look at contextual help, one of those options that we see is the frequency option. So we can set the frequency for this probe. So let's do that. Let's say frequency. And if we look at contextual help, you'll see that that is set in seconds. So maybe we want to set this for every 3 minutes. Whatever the case is, we can do that. In my case, I want to see some results pretty quickly in my output since we're testing this out. So I'm going to set it fairly low. I'm going to set that to 10 seconds. And I'm going to hit enter to complete that. Now, you could run any additional subcommands that you wanted to there. If you want to set thresholds, if you want to set timeouts, you just run those commands the same way under this ICMP echo configuration mode. But in our case, I'm going to leave it just like that. And I'm good there. I'm going to go back to global configuration mode. And now that we have our IPSLA configured, we need to actually start our probe. If we say IPSLA and we look at contextual help, at the very bottom or towards the very bottom, we're going to see the schedule keyword. And that's going to allow us to schedule the parameters for each of our IPSLA operations. We need to, again, follow that with its own entry number. So I'll say 1. And then we can see our other options that we have available. We can say start-time. And a few things we see there. We can set this probe to start after a certain amount of time. So say 5 minutes from when we enter the command. We can set a very specific start time, even down to seconds. We can make that pending so that it's activated, but no information is collected. In my case, I'm going to say now to start this right away. And if we look at contextual help again, we can say recurring. We see that option here. If we want to run this operation every day, we can age that out from memory after a certain interval, or we can set a lifetime value. I'm going to say life and look at those options. And again, you can set the life to a certain amount of seconds so that it times out maybe after an hour. In my case, I'm going to say forever so that that probe will continuously run. If we back out now and say show IPSLA configuration number 1, we can see our configuration output. And we see that this IPSLA is entry number 1. We see that at the top. We see that our operation it's performing is ICMP echo. We can see the target address of 10.0.0.6. We can see our operation frequency is set to 10 seconds. We see the start time has already passed because we have already started this probe. We see the life is forever, and we see the age out time is never because we set that to run forever. So we see all of those things. And let's see if we complete our output. Yeah. Number of statistic hours kept. We see those. We see our all kinds of our statistics here. So now let's go ahead and run the command show IPSLA statistics. And here we're going to see a more basic output. When we see that this is for IPSLA operation ID number 1. Of course, I only have one configured at the moment. This is going to let us know. We see our latest round trip time. We see the latest operation return code, which was an OK code. We see the number of successes, which was 6. And we see a couple of number of failures as well. And that's probably because I set my interval too short. So if we run that again, we see that the successes are incrementing up, but we don't have any additional failures. So probably just because I set my frequency so low, you definitely probably wouldn't do that in a normal environment. Now let's mimic an unreachable condition. Let's go to router 2. And let's go under interface gig 0/2. That's the interface where our server is connected. And if I say shut to shut down that interface, this is going to essentially sever our connection to the server, and it's going to break our IPSLA that's happening over here. So let's again say show IPSLA statistics. You see our latest operation return code is a timeout, and our failures, of course, are incrementing up. If we run that again, we can continue to verify that. No connection /busy /timeout. Now, this IPSLA would be sending out a trap message about these failures through Syslog, which would be handled by a Syslog server, and an administrator would be alerted depending on how we've configured this. But again, this is where we can see that on our local router with a command that we just looked at. We can see again our latest operation return timeout. We see our number of failures continuing to climb. We're already up to 8. Again, timeout code. So not a lot of information here as far as looking at it from the router itself, which again points out why you want to use a server for collection. But we can see the failure. We can see that at least. But a good Syslog server is going to be much, much more helpful when alerting about IPSLA violations. So that's a quick look at basic IPSLA configuration using the ICMP echo function to monitor the reachability of a network device. All right. That is a lot. That's a lot going on. So that brings us to the end of our ENCOR topics. We're going to jump into some ENARSI topics, and most of our ENARSI topics are going to be command line. The large majority of that are going to be BGP. I hope we get through them all. We've got a lot to do still and a little bit of time, so we're going to jump into some BGP topics without much delay. We've got a lot of stuff to try and cover, see if we can get through it all. Let me jump over to our slideshow. So our first topic are BGP states and timers. When neighbor adjacencies, those are necessary within BGP if we want to exchange routing protocol information. But we know that dynamic neighbor discovery is not used. In other words, broadcast or multicast messages aren't used. Instead, we manually configure our neighbors so that BGP can use TCP port 179. And pardon me just a moment, making sure my lab is still coming up well. All right, there we go. Make sure we're good to go. Okay. All right. So when BGP routers are forming a neighborship, we have 6 different states. So let's examine each of those. The first state is the idle state. If we have 2 routers and we're configuring BGP between those, when we set that up locally and enter a BGP neighbor command pointing to a remote BGP router, we go into the idle state where we are actively trying to establish a TCP connection over port 179 to a BGP peer. Also, when we're listening for new connections from a peer router, once our router is in the idle state and we've tried to initiate a TCP connection, our router moves to the connect state. The connect state is where we're waiting for the TCP connection to be completed. So we have a 3-way handshake that's taking place because remember, TCP uses a 3-way handshake. We're going to wait in this connect state for 120 seconds, which is what we call the connect retry timer. This is a value within BGP that is hard set, and we cannot change that. Depending on what happens with this timer, is going to determine the next state that we move into. So let's say that we sit in the connect state for 120 seconds and we have no successful TCP connection, and our connect retry timer reaches 0. Why might this possibly fail? Well, that could be because a QoS rule, or maybe we're dropping TCP traffic due to an ACL, maybe we've incorrectly configured a neighbor IP address, lots and lots of things. But essentially, if we have an error here that allows our connect retry timer to decrement all the way to 0, if 120 seconds go by, then we move to the active state. The active state is where the router will actively try to establish another TCP connection with a peer. This will last for 120 seconds, and if we fail here, we go back to the connect state and we start over. If we're successful, then we move to the open sent state, which we'll discuss in just a moment. So if we're having a TCP connection issue, our states are going to loop until we can correct that. So I tend to think of these first 3 states as the TCP phase of BGP. I just kind of mentally lump those together. This helps me to remember how all of those work together. So that's just a tip for you. If you seem to be stuck in one of these states, it's a TCP connection issue. So let's say that our TCP connection is successful from the active state. Then we move to the open sent state. This is the first state where we actively start to send BGP related messages. So you can maybe see why I make that mental separation between those first 3 states, because they're reliant on TCP information. We send out an open message from our originating router to a remote BGP router, to a remote BGP peer, and we're waiting to receive a similar open message back. That message contains important BGP information that is compared between our peers, such as the BGP version, the source IP address of the open message, the autonomous system number, the BGP router ID, and of course our security parameters such as the password. If the initiating router receives an open message that matches, then BGP will begin sending a keep alive message to keep that session established. But before we talk about a successful connection, let's look at what happens if we have a failure. If the open message information received does not match, then a notification is going to be sent to a peer, and that will signal the teardown of the BGP session. This will take the router all the way back to the idle state where we would start over. Now, it's worth noting that we do not tear down the TCP connection. We only tear down the BGP session. So although we're all the way back to the idle state, we'll quickly move back to the open sent state. So if you're bouncing in and out of open sent, that's a good indicator that something in your BGP configuration probably doesn't match. Now, assuming that everything does match, assuming that we're able to establish a BGP session and we're waiting for keep alive messages to be received, if we do not receive those, then we're going to move all the way back again to the idle state, and we're going to begin again. If the peers exchange keep alive messages successfully, we move to a state that we ultimately want to see our BGP enabled devices in, which is the established state. This is where we send update messages and keep alive messages between peers. This is where we finally will exchange prefix information through update messages, and we'll also continue to exchange keep alive messages to make sure the session remains established. By default, that keep alive interval is 60 seconds and the hold time is 180 seconds. Those can be changed if desired, of course, but those are the default values. As I do with those first three states, I like to categorize these together on their own. I call these the BGP phase. So if we see a router stuck in one of our first three states, idle, connect, or active, then we can consider that to be a TCP-related issue when troubleshooting. But if we're bouncing around in those last three states, open sent, open confirm, or established, then you should start troubleshooting the actual BGP configuration. So let's look at a BGP lab now. Let's look at BGP multi-hop. By default, when we use eBGP, this requires two Cisco routers to be directly connected to one another. If not, they're going to fail to form a neighbor adjacency. And the reason is because eBGP uses a TTL value, a time to live value of 1 for BGP packets. The value, we know that each time a packet traverses a device, our TTL value is decremented. So once that reaches 0, the packet is, of course, dropped. So you can see that with a TTL value of 1, if the BGP routers are not directly connected, that packet is going to be discarded. So that's going to be a problem. If you look at our topology here, you'll see that we have three routers. We have R1 in autonomous system in AS65100. We have R3 in AS65200. The middle is a non-BGP router, rather. And so this is a special case where we might need to use something called BGP multi-hop because we see that these two BGP routers are not directly connected. And I also point out that this command is only used with eBGP and not iBGP. So let's jump out to a live interface. Let's go get connected to our router. First thing on router 1, let's create some static routes because right now we're not going to be able to reach that. Let's go under global configuration mode. Let's say IP route. We want to do 20.1.1.2. And the next hop address is 10.1.1.1. That's the R2 interface that we're connected to. Let's go to R3. Let's do something similar. Okay, let's just quickly make sure I can ping router 1, and I can ping router 1, so that's good. Let's go to R1 now, and let's create our BGP instance. Let's say router BGP 65100, and let's configure a neighbor. We want to say remote -AS. Oops, sorry. I actually want to call out the IP address first. 20.1.1.2, remote autonomous system. That's going to be 65,200. And then back on router 3, similarly, let's say a router, BGP. Our autonomous system is 65,200 here. We'll say neighbor, 10.1.1.2, remote autonomous system, 65,100. Now, in most cases, that's a normal working BGP configuration. But again, we're not directly connected. If we break out of here and say show IP BGP neighbors, you'll see that it's told we have 0 active neighbor sessions. And we see that, in fact, let me break out of this command and let's say show IP BGP neighbors include external. It's going to tell us that external BGP neighbor is not directly connected. And again, let's look at our state. I didn't point out the BGP state. It tells us the BGP state is idle. That means we're waiting for a start event. We see 0 active sessions. And again, that's because we ran into an issue where our TTL has expired. We can overcome that by eBGP multi-hop. So let's go back to router 1. We'll do it from this side. So we're already under router BGP 65,100 configuration mode, and we can use our neighbor command again. So we'll say neighbor 20.1.1.2, and the option we want is eBGP-multi-hop, and we can follow that at the end by the maximum hop count that we want to use. We can use anything between 1 and 255. Now, it's important to note here that you, if you don't specify a value, it's going to default to 255. So it's a best practice to actually designate what you want there as far as security reasons go. You really don't want a maximum hop count of 255 in this case. So I'm just going to set that to 2, and I'm going to hit enter. And over on router 3, I'm going to do something similar. Under router BGP 65,200, go up to my neighbor command, and I'll say eBGP-multi-hop 2. And once we do that, we're going to, let me break out of here. And once we did that, you'll notice that we did have a neighbor adjacency form. We saw a BGP neighbor come up that we didn't have before. So now, if we say show IP BGP neighbors, now you'll see that our BGP state is established, just as we would expect. And we see our uptime as well. We've been up for roughly 13 seconds when I ran this. We also have 1 active neighbor session. So that's a very simple way we can use eBGP multi-hop to traverse a non-BGP router in the network. It's possible that you have a router at the edge of your autonomous system that you're trying to connect to, and that's a case where we might use BGP multi-hop in the real world. Let's talk about BGP route reflectors now. Let me jump into that one. Let's talk about why we might need to configure a BGP route reflector before we actually do that. You can see that we have 4 routers here in this particular topology. We have router 1 in autonomous system 65,100. We have router 2, router 3, and router 4, all in autonomous system 65,200. And I've already configured on this particular network. I've configured BGP, so that's all done. I have a very basic BGP configuration in place containing both eBGP and iBGP neighbor adjacencies. So let's talk about the way iBGP neighbors work. By default, on a BGP-enabled router that receives an iBGP route, or in other words, if I learn from another router in my own autonomous system, if I learn a route from that, I'm not going to advertise that to any other routers within my same autonomous system. I'm not going to do that. So let's go out to our interface now. And you can again see our topology here for our route reflectors. Let's go to router 2. and we'll say show IP BGP. We can see our BGP learned routes from here. We can see that R2 has learned about the 10.1.1.0 network, which we can see from the topology is the loopback on router 1. We can see that this was learned from another autonomous system rather than the one R2 is in. Since that's true, that's going to be advertised to R3. We should see this 10.1.1.0 network on R3 because it was learned from an autonomous system other than the one R2 is in. So let's go to router 3 and verify that. If we say show IP BGP, we do in fact have knowledge of that route. We see the 10.1.1.0/24 network that was shared from router 2. Notice the lowercase I that we see. Notice that. That tells us, if we look at the status code, that this was learned via iBGP advertisement, an internal BGP advertisement. This means the route will not be advertised from router 3 to any other routers in this same autonomous system. So R4 should not know about this route. Let's verify that. Let's say show IP BGP on R4. And in fact, we do not have knowledge of the 10.1.1.0 network. Also notice the 20.1.1.0 network is also missing because we have the same scenario. R3 learns this route from R2, but R3 is not going to advertise that to other routers within its own autonomous system, which is, of course, router 4. R3 learned those from an iBGP neighbor, which is R2, but it's not going to pass those on to other iBGP neighbors. Now, you might be thinking, well, we can just really easily fix this maybe by making R2 and R4 neighbors. If we do that, we can create a full mesh within the 65200 autonomous system. But if you scale that up, that's not scalable at all. So what we can do instead is use a route reflector. Specifically in this case, we're going to configure R3 as a BGP route reflector. So it's going to, any routes that it's learned from an iBGP neighbor will be reflected to other routers within the autonomous system. So that means once we do that, the routes that we see missing on R4 should be visible here. So let's go to R3 under global configuration mode. Let's go under our BGP autonomous system, which is 65200, and we're going to issue an additional neighbor statement for each neighbor, stating that each neighbor is a route reflector client. So we want to say neighbor 30.1.1.1, and we want to say route hyphen reflector hyphen client. So we're pointing to R2 from here, and we're telling it R2 is a route reflector client. Let's do the same for R4. And as we did that, you'll see that we had a console message saying that our adjacency went down and came back up. Our session was rebuilt. That's totally okay. So we'll say neighbor 40.1.1.2 route hyphen reflector hyphen client. We're going to see that session rebuilt again. Now, let's go back to R4. We see our adjacencies changed. If we say show IP BGP, now you'll notice that we have learned two additional networks. Now we do know about the 10.1.1.0 and 20.1.1.0 network. So we see those. Those are being now reflected to R4 from R3. So that's a quick look at why we would need a BGP route reflector and how we can very, very easily configure those. Let's go back to our slides and we'll jump into BGP route summarization. We also call route summarization, by the way, you might also hear that referred to as BGP aggregation. So first, let's look at this topology. We have router 1 in autonomous system 65100. We have routers 2 and 3 in autonomous system 65200. And you can see that on router 3, we have 4 networks in place. We have the 10.10.0.0 network. We have the 10.10.1.0, .2.0, and .3.0. So again, we have 4 networks in place on R3. R2 connects to R1 over the 20.1.1.0 network. In this case, R2 is our autonomous system edge router sitting at the edge of autonomous system 65200. And this router, router 2, this is going to aggregate all of our 10.10 networks in a summary route over to the AS65100. That's the goal here. So let's get connected into that interface. Let's look at our current configuration. Let's say show IP interface brief, and you'll see all of our, we have all of our loopback addresses here. We have 4 loopback addresses dedicated to these 10.10 networks, as we would expect. Let's say show run, begin the section starting with router BGP, just to see our current BGP configuration. You can see we are advertising all of these prefixes into BGP, all 4 of our 10.10 networks. Let's connect to router 2, which is our that's our edge router for AS65200, and let's look at our BGP table there. Let's say show IP BGP, and just as we would expect, we have all 4 of these prefixes advertised from R3. What about R1? Let's go to R1. Say show IP BGP. Take a look at that BGP table. And just as we saw in R2, we see all 4 of those prefixes. So now what we want to do, let's look at how we can aggregate our routes on R2 and advertise these to our neighboring autonomous system, which is where router 1 is at. Now, in order to do that, we need to know how to calculate the correct route summary address. And there are certainly calculators online that will do that for you very quickly, but it's still important that you understand exactly how this works. So let's really quickly just take a look at that. You can see here that first we want to convert each of our network addresses to a binary value. If we take all of our 10.10 networks and we convert those, you can see the values that we get. And we want to look at the common bits. In other words, how many bits do these addresses have in common that are exactly the same? In this case, we have 22 bits in common. The first 16 bits plus an additional 6 bits, which makes 22. So that means our network addresses are going to share the first 16 bits, which would be 10.10.0.0 with a /22 mask. In other words, 10.10.0.0 with a mask of 255.255.252.0. So this is a prefix summarization that summarizes all 4 of our networks on R3. So that's what we want to use as our aggregate address. So let's do this. Back on R2, let's go under router BGP 65200, which is our local autonomous system that's running. And the keyword we want to use is aggregate-address. We want to follow that with the summary address that we calculated, which was 10.10.0.0, subnet mask 255.255.252.0, or in other words, a /22 mask. So if we hit enter there, let's break out and say show IP BGP. And we do see all 4 of our networks that we saw previously, but we also additionally see our aggregate address being advertised as we would expect. Now, if we go to R1 and say show IP BGP, what are we going to see? Well, we're seeing the same thing. We see all of our original 4 networks plus our aggregate address. So we need to suppress our original prefixes that are being advertised. And we can do that by going back to R2. And let's go back under router BGP 65200. And we can say the same command, aggregate-address, with our network and subnet mask. But this time we can add the keyword summary-only. So when we do that, this is only going to advertise our aggregate address. If we say show IP BGP, of course, on router 2, we still see all of those. But now on router 1, notice we only see a single prefix being advertised in there. And of course, we see the next hop, which is 20.1.1.2, which is where that's coming from. That's exactly what we want to see, only the single prefix advertisement. If we say show IP BGP, and we say 10.10.0.0/22, this is going to give us a little bit more detailed information. Here we can see that we have the aggregator. It's telling us this was aggregated by Autonomous System 65200 by router 2 at the loopback address 2.2.2.2. That's the router ID over there. We can see that also at the end that this is listed as an atomic aggregate. So what does that mean? That means that this is one of our well-known discretionary attributes for BGP. This is essentially just informing this router 1. It's alerting this BGP router that this actual route technically does not exist, but that it is a generated route representing a contiguous group of addresses. So again, just to show you that main output, we only have the single prefix being advertised. So that's how we would do BGP summarization through an aggregate address. All right. Well, we are at the 4 p.m. mark. I want to thank you so much for sticking with me. I hope you've enjoyed this training. I hope you found it useful. I know some people had to already dip out. Lots of different time zones happening here. But again, we'll have this replay up so you can see that. And thank you for all the kind words to everybody who's just sending thanks for the training. It's been my absolute pleasure. I saw a couple of people had jumped over and subscribed to my own YouTube channel where I'm doing CCIE studies. So thank you so much for that. Thank you for checking out what I'm doing over there. Thank you for spending a couple of hours with me today. I hope you found it useful. I hope you have a wonderful rest of your day or evening. Thanks for spending time with me, and I'll see you again very soon.